So on our equation, it said Zwitter ions. Some molecules have two acid-base functionalities, and depending on the solution, we may be protonated or deprotonated for those varying states. So this is a super common question in biochemistry, because in biochem we're running at physiological pH, which then means we have to be able to predict how that affects the structure. All right? So we'd have to look at our functional groups, determine pKa's, know our pKa's, know what pH we're at, and do those fair comparisons across the board to then come up with structural effects. If your pH is large, what does that mean? Acidic or basic? Basic. Means you're basic. Our pKa is kind of our center point on where we're comparing from. That's our species. So if we are more basic than our pKa, that means I need to remove the hydrogen. So I need to be in the deprotonated state. What happens if the pH is very low? Well, then I'm acidic. So if the pH, again, to our 0 point, which is our pKa, the pH is lower than the pKa, then I need to be in the protonated state. Most people are able to nail down the carboxylic acid functional group relatively well. Right? If we're at a pH of 1, right, what should my protonated or deprotonated state be? Well, if we compare it to the carboxylic acid has a pKa of 2. So I'm at a pH that's less than the pKa. I need to be in the protonated state for the acid. Well, what is the protonated state for the acid? How we always draw it, right? It's exactly as shown. Okay. What happens if I then switch this up to a pH of, say, 4? Well, the pH of 4, I'm then at a pH that is greater than the pKa for the carboxylic acid, so I need to be the deprotonated state for the carboxylic acid, which just means removing the hydrogen. If I move up to a pH of, say, 10, what happens? Well, I'm still greater than the pKa. It's the deprotonated state still. Okay. What happens when we switch through to the amine, though? And that's where things get a little bit wonky. What is the pKa of the amine? And this is, I'm actually going to start over on the other side. What is the pKa of the amine? This was the tricky one that we told you got to watch out for in memorization. 9 and 35. 35 is such a large value, it is actually outside the realm of possible protonation or deprotonation states in the solvent of water. Okay. In the case of biochemistry, what does that mean? Well, the pKa of 35 then is irrelevant. Okay. The pKa of 35 is referencing removing a hydrogen directly from the amine. Okay. So we'd be forming a negatively charged nitrogen. That is not a stable structure. That's why the pKa is so large. The pKa of 9 that everybody then references becomes a little bit trickier to then manipulate. So if I'm at a pH of 10, at a pKa of 9, okay, a 10 is higher than the 9, I need to be in the deprotonated state for the amine. What is the deprotonated state of the amine? What is the deprotonated state? NH2. Okay, with the carbon technically connected to it. We're in the deprotonated state. Okay? So when we draw an amine, we're typically drawing the neutral structure. Okay? What we have to be aware of is what its protonation and deprotonation states are. The deprotonated state is the neutral one. The protonated state is the charged one. Okay? And that's a significant difference from our carboxylic acids. Okay? This, again, kind of confusion, I think, stems from we work with acids a lot, we don't work with bases so much. You've worked with carboxylic acids super frequently. Pretty much everything you did in Gen Chem, anything that involved anything interesting, involved a carboxylic acid. So you're used to dealing with those structural states. Okay? You aren't used to, or as used to dealing with basic molecules. What happens if I now drop to a pH of 4? Well, I'm now more acidic than the pKa of the amine, which then means I need to be in the protonated state. What's the protonated state for the amine? That's with that extra hydrogen, the nitrogen becomes positively charged. Kind of makes sense? So it's knowing what the protonated and deprotonated states are for your common functional groups. Okay. Sometimes they're easier than others, like the acids. The amines aren't so easy. We have to watch out for them. They can get a bit tricky. Okay. Super relevant for biochem, a little bit less relevant for us because we change the reactivity because we get to dictate the solvent. In biochem, we don't get to dictate the solvent because, well, if we change the solvent, our organism dies. Right? The whole point is to study the living organism. Right? So, chapter 7, a couple extra little tidbits come out of it. You should have watched the video that went through and looked at all the different mechanistic steps. But then I also went through and kind of summarized some analyses when we're looking at electron rich and electron poor. Largely because I think the question that SmartWork asks about electron rich and electron poor is kind of confusing. I mean, I can get the answer, but I don't necessarily trust it so much. So that's what this slide is supposed to help with. We're largely looking at differences in electronegativity. If I have an electron-rich atom, it will by definition be an electron donor. Okay? What atoms are electron donors? Well, typically things that have negative charges are good electron donors. Okay? That would be your Lewis base, your Bronsted base, and your nucleophile. Okay? The electron-rich atoms are typically high in electronegativity. Okay? And that, I think that's Chi, is the symbol for electronegativity, which I never remember in which class if I've mentioned it. Okay, so there it is. Chi is our symbol for electronegativity. Why would atoms that are typically high in electronegativity be electron rich? The whole point of having a high electronegativity means that you've attracted electrons towards you, which means you have a lot of electrons. That by definition makes you electron rich. Okay? When we're looking at our electron rich atoms, they will be nonmetals. Okay? We can hide those electron rich atoms or some of the electron donor or negative charge aspects by bonding them to a metal. So for instance, if I drew out hydroxide, you should be able to tell me that that is an electron rich atom. Why is that, or why is the oxygen an electron rich atom? Negative charge. Okay? Typically high electronegativity. All of that matches. So that is now too easy of a question, so we make it more difficult by hiding the negative charge with a metal. And now we go, oh, now I can't figure it out because there's not a negative charge. Okay? It's a very simple way to hide that chemistry from you. Anytime you see an ionic bond, you should immediately cleave it into the ions. Then you can evaluate those ions and decide should they even form bonds. Sodium, which you should know from both 151 and 152 solubility rules, always soluble, meaning it's always a spectator. You'll almost always see me ignore sodium ion, okay? Which is kind of a bad habit when it comes to drawing out reactions because I won't show that counter ion and yet you typically see it in your homework or exams. Okay? So I'll try to make sure to include it or add it back into our structures. Again, we can immediately eliminate it because it doesn't do anything. Okay? The electron poor atoms. These are electron acceptors. They're typically positively charged because they don't have any electrons. They must be positive. These are Lewis acids, Bronsted acids, and electrophiles. They are typically low in electronegativity, okay? Like hydrogen. Oh, hydrogen was a Bronsted-Lowry acid. Okay? They're generally electron poor because they've lost all their electrons. Okay? They're bound to something that takes the electrons away. Where we run into an issue with our electron poor on identifying how we can hide these, for instance, if I showed hydrogen as positive, let's color code. Hydrogen is positive, you say, okay, well that's electron poor. How do I hide the fact that I have an electron poor atom? Well, now I don't have a positive hydrogen floating around, but by bonding the hydrogen to a highly electronegative atom, I should recognize that I now have a strong acid. That hydrogen becomes very positive. HCl is an electron-poor molecule. It's giving me lots of hydrogen, or positive charge. Why do I ignore the chloride? Okay. For the chloride to act as an electron donor, what has to happen? It would have to share the electrons outwards, which would then mean how many bonds does it have? Two. Can it have 2 bonds? No. As you were just addressing, though, Sam, what's going on? You said for one of your options here was to take electrons from the hydrogen. If we do that reaction first, now chloride, Cl minus, can act as an electron-rich atom. But I have to break that bond first. Okay? Kind of makes sense? So there is for sure a question, probably in the Chapter 7 Smart Work. I think it's one of the first ones. It had some weird kind of oddball questions in it. They're kind of coming back to this and trying to classify those molecules as best as possible as electron-poor and electron-rich. Okay? It is helpful, though a heck of a lot easier to do when you're given a reaction. Just given a molecule, it can be very difficult to nail some of those down. The other thing that comes out of Chapter 7 is another intermediate, okay, in reference to what's known as the Keto-Enol, officially tautomerization. This is a big preview for second semester chemistry and for anybody that has to move into biochemistry. The Keto-Enol tautomerization is one that is ultimately responsible for almost all biochemical reactions. Okay, so it is an important intermediate to be looking at. If we go through and take a look at this structure here, we have 2 basic sites. We have the oxygen with a lone pair of electrons, which could act as a base. We also have the carbon with a lone pair of electrons that could act as a base. Okay. So if I now react this with an acid, where do I expect the hydrogen to go? Because they're resonance structures, both of them exist. So I have to decide which one is the best one to react. Well, maybe I get the same product. What would the product be in the top case? And I would expect NOH. In the bottom case, what do I have? What's the functional group on the bottom one? It is a ketone. It's a little bit convoluted because we didn't specify what that atom was, but let's go ahead and add that C. Hopefully that now establishes that we have the ketone on the bottom. What is the functional group that we have on the top?
Alcohol.
We have an alcohol. Is that all we have there? Whoa, I can't spell alcohol. And we have an alkene. Okay. So we have an alkene and an alcohol and a ketone, and yet the name that we're referencing here is this called Keto-Enol. Okay. We actually have a new functional group in the top one. It's not an alkene and an alcohol. Okay. For the same reason that if I look at, say, this purple one, what functional group do I have now? Why are you calling that a carboxylic acid and not an alcohol and a carbonyl?
Because the carbonyl and alcohol.
When the carbonyl and the alcohol get close enough to each other, the chemistry of both of those functional groups significantly changes. Changes to the point where we call it a carboxylic acid. Why is that then relevant when we look back at the alkene and alcohol? They're right on top of each other. The same thing happens. That is no longer an alkene and an alcohol as separate functional groups. That is actually a new functional group. That functional group happens to be an enol. Okay? So when we're referencing, we'll get back to that, the Keto-Enol, what they're talking about is that we can oscillate back and forth between the enol form shown on top and the keto form shown on the bottom. We will oscillate between those two by going into the intermediate shown on the left. That intermediate is no longer an alcohol because we've lost that hydrogen. Okay. What happens to an oxygen that loses a hydrogen? We call it it's a little bit harder. When we add carboxylic acids and we remove the hydrogen, what is the resulting conjugate base referred to as? Maybe some people have heard it, some people haven't. A carboxyl 8. When we remove the hydrogen, it's no longer an alcohol. Okay, so we can't call it an alcohol. We'll call it an enol 8. There's the ending because we removed that hydrogen. We're now in the basic state. Okay? So our enol can tautomerize or change its structure to the keto form. Okay? This becomes a bit tricky because if those two structures are now in equilibrium with each other, well, what's the answer? Okay? We can't say both because they are significantly different in energy. One is correct, the other one is incorrect. So we'd have to come up with the reasons for why one is better than the other. Okay? The textbook goes into some gory details of bond energies and other fun stuff like that. I would take a step back from that and try and decide where we would prefer to have that hydrogen located. So where's the most reactive atom in both those structures? Yeah. The oxygen. Why are you saying the oxygen is the most reactive? And this is the most electronegative. Okay? We might say the pi bond, okay, or the alkene, but the alkene doesn't show up in both. It's really just the oxygen. And we're deciding where those pi electrons should oscillate. What is the difference between the oxygen in the top structure and the oxygen in the bottom structure? Double bond versus single bonds, we can do better than that. Could reference the hydrogen, we can do better than that. No. So let's shout that out a little bit louder for everybody else to look at. SP versus SP2. Our hybridization is different. Is it SP versus SP2? It's SP3 versus SP2. What is our difference between those? Okay, the number of p orbitals. Which one is more electronegative, the SP2 or the SP3? SP2. If we go through and look at oxygen, say, here you go, oxygen, you can choose your state. You can either be SP3 or SP2. Which one is it going to choose? Why SP2? What's that? Nope, has the same number of electrons.
Electrons can freely move or have a bigger area.
In the SP2, more electronegative. What is oxygen? The second most electronegative element. Where is oxygen going to prefer to be? Where it has the tighter hold on electrons or the looser hold? The tighter hold. That makes sense for the keto form to dominate. The other way you can remember is it's called a keto-enol. Right? Why? Because the keto form is more important than the enol form. Right? So if you're drawing out a reaction and you happen to produce an enol, you should immediately go, oh crap, it's no longer the enol, I need to make that the keto and convert it across immediately into the ketone. If we are lucky, we will see that at the end of this unit. We'll probably have to see it in the beginning of the next unit, just based off of time. Okay? So this is what our textbook goes through and looks at all the bond energies. You can be, oh, like it's more stable. And I find that confusing as all heck, largely because there's a bunch of numbers in it, probably. I would just look at kind of the hand-wavy answer of our hybridization states. That's a hand-wavy. Kind of makes sense? Okay. So we will again see that. Well, let's take a minute. Chapter 6, 7, and 8. So we talked about 6. 6 was our acids and bases. 7 is all of the different mechanistic steps that are possible in organic chemistry minus the radicals. Chapter 8 sort of mechanisms, that's now looking at specific types of reactions and labeling which mechanistic steps are necessary for those types of reactions, which is our substitution and elimination. Okay. The other thing that 6 brought in was energy diagrams. So we looked at this already, and we labeled added curved arrows and the type of mechanistic steps. Now what we should try and do, let's provide an energy diagram to describe what is going on within this. Okay. A few people have already attempted this. In fact, most people should have already attempted something along these lines based off of the homework, lab, or lecture. So see what you can come up with. I'll give you a couple minutes. Talk to the people around you. See what you get. So we'll start off with our reactant, our very first one. Might be helpful to say reactant 1, 2, 3, product. Since I don't really know where I'm going, I'm going to say the reactant right about there in the middle. Okay. I want to look at that very first step, going to 1. So I want to establish the energy level of 1. Should 1 be higher or lower in energy? Higher. Why are you saying higher? Okay, it is charged in comparison back, so we could put 1 higher up. So we can then go through and say, doop. There's our step. Okay. In your referencing of saying 1 was higher in energy, and this is a kind of a personal issue I have with looking at our reactions, our energy diagrams, is it's all going to depend on your frame of reference. In that analysis that we just did to say 1 was higher in energy, we evaluated the organic molecule on each side, which would say this reaction is endothermic. What type of reaction was this? What was it? That first step. What type of reaction? Yes, it's non-spontaneous. It's an acid-base step. From Gen Chem, acid-base steps are always exothermic, and yet somehow we're showing this as endothermic. The reason we're showing it as endothermic is because of our frame of reference. We are referencing these two molecules. What happens if we also interpret the energy of the acid in my reactant side? Well, now what happens? You do get an exothermic result. 1 will be lower in energy because reactant H plus is missing its octet. Okay. So your acid-base reactions are officially always exothermic. It can be a bit tricky in those interpretations. Officially it's exothermic. You should be showing it exothermic. I find that kind of a hard analysis to work through. I would probably show it as higher, okay, because of that charge state. Okay. Just realize that is technically wrong. Okay. It's all a frame of reference on how much we're bringing into our analysis. Ideally, you should focus on the organic molecules. So we now have a new question. We're now moving from 1 to 2. So take a look at, compare those structures, and decide what you would expect to happen. I kind of feel like my arm is twisted and I gotta put 1 as a lower energy, that's an exothermic reaction, because it is an acid-base reaction. I will grade you fine both directions. In the case of drawing an energy diagram, you should provide an explanation for what's going on within it. Okay? So that way, if you do place it in the wrong location, but you give me an explanation that makes physical sense, I'll be like, okay, I understand your frame of reference. I can now accept points for that or not. If your explanation is wrong and your energy levels are wrong, well, then, yeah, you lose everything. Right? So 2. Where would I expect 2 to be relative to 1? So we've heard lower and higher. Why would we say lower for 2? So positive charge on carbon instead of oxygen. Oxygen doesn't want to be positive because electronegative, so that's not a bad argument, except what trumps where the charge is located? Octet. We have to make sure our Lewis structure is valid. Carbon, or structure number 2, we are missing an octet on that carbon, which necessarily means it is higher in energy. Should it be higher in energy than the reactant or lower in energy than the reactant?
Higher.
Why higher? Because there's a charge and and octet. Okay, so lots of reasons why it too should be higher. What about 3?
Lower, lower than
3 versus 2. They're both charged. They're both missing their octets. Which one's more stable?
3.
Why is 3 more stable than 2? Because it's a tertiary carbocation as opposed to a secondary, which means I should be dropping in energy to 3. Should 3 be higher or lower in energy than the reactant?
Higher.
Why higher?
Octet and charge.
Octet and charge. That is higher, right? And then product. Where should the product be?
Lower than 3.
Lower than 3 because
Octet satisfied, no charge.
octet is satisfied and no charge. Lower than 1? Why? It's not an octet. Probably charged, which then also means, by definition, lower in energy than our reactant. And our product is very likely to be the lowest energy thing. Okay? Within this, what I expect you to be able to do is look at each of those relationships and say, this should be higher than this, lower than this. I don't expect you to label those peaks and nailing down which activation energy is necessarily, not necessarily activation energy, but the transition state. Which transition state is higher or lower than another. I just kind of expect you to connect the energy wells. I don't really care about the height of your transition states. Okay. Notice that I've got that last one a little bit lower than all the others. It's just kind of arbitrary. So take a look at 2 and 3. In 2, what is the reactive thing? The what? The carbon that is charged, so the positive charge is the reactive thing. Okay? And we could say that the positive carbon. What's the reactive thing in 3? Positive carbon. Well, there's now no difference at a superficial level, so we have to look deeper. When we look deeper, what's the difference? This carbon is connected out to 2 carbons, and 2, and in 3, that carbon is connected out to 3 carbons. So what we're looking at as a difference is a secondary carbocation versus a tertiary carbocation. I say, okay, well, which one's more stable? That goes back to what we talked about on Monday. There's more electrons coming from those outermost carbons. Those can better stabilize that positive charge, which means the tertiary is lower in energy than the secondary. That establishes those lines. Does that make sense? Okay. And we now have an energy diagram that roughly depicts what happened within this mechanism. Okay? Whenever you're looking at a reaction and trying to predict should this thing have happened, and this is where everybody won't be pretty happy with it, what can you do? You could draw out an energy diagram of all the possible reactions and say, well, which one of those is most likely to happen? You may not be happy with that, but it works. Okay? So, for instance, let's take a look in the transition between 2 and 3. Couldn't I, instead of taking the hydrogen and doing a rearrangement, that undid a lot. Couldn't I have taken this carbon? Everybody see that mechanistically? I want that back. Couldn't I have done that curved arrow to get the carbon shifting over? Is that not a valid mechanistic step? Sure. What's the result? So there's just the atoms that were there. What happens with charge? Still needs to become charged. Where's the charge? That position, right. Okay. In this new structure, they're both secondary. So if we added this into my drawing, I'd be putting an arrow here or an energy here for this new intermediate. Let's call it N. Which is more likely to form, N or 3? 3 because lower energy. Couldn't I have just as likely taken this hydrogen? Isn't that also a valid rearrangement? What would the result be? Well, I have that new hydrogen over there. There was already one there. And as Mohammed noticed, that would mean this carbon is positive, and I'd have what kind of a carbocation? A primary, which is higher in energy. So there's my primary. Which is most likely to happen? I know that's really ugly there. Our primary, our new 1 or 3? 3, because lowest energy. Okay. Okay. Our activation barrier for 3 is the smallest. Does that make sense? So we can look at all of those possibilities. And yes, as you look at more and more possibilities, it turns into what I've got drawn here, which is a giant confusing mess. Right? So when looking at a question, particularly now or this week or maybe even this weekend, use a giant sheet of paper and draw out your energy diagrams. Okay? And start to say, well, couldn't I have done this? What would that have resulted in? This is why the curved arrows are super, super important. Because as long as you do what the curved arrow says, you can draw an appropriate structure. With that appropriate structure, you can now evaluate energy. With the energy, you can now evaluate, should that have happened? Okay? Or is that likely to happen? So why did I put the product at that low energy? I'm going to hold on to that for a second. What was your question, Farzan?
So why is the activation energy for number 3 lower than the other ones?
What happens with N being the exact same energy? Its activation barrier is going to be slightly higher. So there's not a large difference there. Okay? 3 is going to be dependent solely on the energy of our reactant due to the Hammond postulate that we talked about. N is now going to be somewhere in between. It's not going to drop lower than that because, well, that's already pulling the activation barrier lower. Okay? So N being the same energy as 2, the activation barrier is going to be a little bit higher. Not a whole lot. So is the speed of the reaction going to become relevant there? Probably not. What is going to become relevant is the thermodynamics. 3 thermodynamically is favored over N.
Also, if you look at the structure for N, that's the exact same structure because you just shifted the carbon and that's the same thing.
I was trying to avoid that, but that's true too. If you take a look at N, N is the exact same structure that we started with before we did the rearrangement. Okay? So we actually didn't transition anywhere. There's no activation barrier. It's the exact same thing we started with. Okay? Back to Amarachuku's question, product. Okay? Why is the product energy lower than everything else? Okay, well, where do you want to compare first? And this is something that always seems to boggle people's mind. I'm not comparing the product energy to everything. I'm comparing the product energy to one thing. Okay, previous step. Should the product be higher or lower in energy than 3? Lower in energy because it's not charged. It's not charged and it's satisfied octets. So the product should be lower in energy than 3, which by definition means it's lower in energy than 2. Okay? Comparing it back to 1. Intermediate 1. All my numbers are gone. 1 now to the product. Which is more stable? Product because? Charge. So my product needs to be lower in energy than 1. Well, if it's lower in energy than number 1, it's by definition lower energy than the reactant. Okay? Kind of makes sense? So it's stepwise process all the way through. We aren't jumping and saying it's lower than everything. It's one thing at a time.
So if the energy was higher, then it would just push it back to reactant, right? To be most
If our product was higher in energy, what does that mean about the likelihood that our reaction occurs? Not very likely. So we would have to try to do something to force that reaction to occur, and we can do that, and we'll see that when we look at elimination reactions. Okay? So if we just clear all that away with that button, what does an elimination reaction result in? The elimination reaction is the removal of something to form a pi bond where I did not have a pi bond. Ignore that I don't have all the proper pieces, but we're making a pi bond. If I compare my product to my reactant, where would I expect my product energy to be? Higher in energy because pi bonds are higher in energy than the sigma bond. Okay? So if we look at the elimination, we would immediately jump out and say, what shouldn't happen? Because the alkene is higher in energy than the alkane. Okay? We can tweak the system to help force the alkene to form through things like Le Chatelier's principle. Okay? And if you're freaking out about Le Chatelier, we're just doing rough comparisons. It's the qualitative, not the quantitative. Okay? After that, we're now full on pretty much into Ochem. Right? I know, we're like, what, 12 weeks in, you're like, now we're starting Ochem? Yes, now we're starting Ochem. You have the basic pieces to build, now you got to build. Okay? The question is, what are your options for building? You get 5 primary reaction types: acid-base, substitution, elimination, addition, and radical. Okay? And I asked about the elimination earlier. Have we seen this slide?
Yes.
Yeah? Oh, good. Oh, in the video it showed up. Okay, so you should have seen it in the video. These are our 5 primary reactions. We will be using these primary reactions throughout the semester. Yes, each and every single one of these. What happens then in second semester? We'll use them again. And instead of running just acid-base, substitution, elimination, addition, and radical, we'll do elimination and addition. And instead of calling that an elimination reaction and an addition reaction, we'll call it pretty darn close. An elimination addition as a new type of reaction. So these are the basic pieces that we will then add and stack. The mechanisms that we talk about are where these things are coming from. How do we build these things from those individual steps? We need the mechanisms because certain repercussions come out of running the reactions. We want to be able to predict those repercussions instead of waiting for it to come up and hit us. Right? So, memorize the basic setups behind these. Recognize what's happening. The text here, I think, is probably the most helpful thing. The structures and pictures are there to kind of draw it, but a lot of people get bogged down in those. Acid-base reaction, what happened? Only transfer of hydrogen. When we look at the reaction shown, what happened? We're going to only transfer to hydrogen. Substitution. We exchanged an atom just like an acid-base, but anything other than hydrogen. Well, what happens? We look at our structure, the same thing's happening there. You will notice within this, we get all sorts of other weird symbols popping up. LGs, nukes, bases, okay? Elect nukes. Okay? Those are in reference to the basic elements and pieces that we've discussed in the past. Okay? LG is probably the only one that's new at this point, which stands for leaving group, because what did it do in the structure or in the reaction? It left the organic compound. Okay? So the names ultimately have some tie back to things we've already worked with. We're trying to look for those common patterns. Once you know the type of reaction, you can then start to evaluate mechanisms. Once you know the mechanisms, you can then start to apply the complications of said reactions. Okay? Like, for instance, chirality. So, here's our big summary, because multiple semesters people said they wanted to know the summaries first. If we take a look at our alkyl halides, which is our simplest version of this, we have substitution and elimination reactions. Those are the only 2 possible reactions for an alkyl halide. Right? Those split into different mechanisms. We have the SN1 mechanism and the SN2 for substitution. Okay? Those will then have a certain rate associated with them. We'll look at what we expect for the substrate. We'll look at what we expect for the nucleophile, what we expect for the solvent. When we talk about elimination, we'll do the same thing. Elimination breaks down into 2 different types of mechanisms, E1 and E2, which means we have a rate expression, which means we have substrate preferences, which means we have base preferences. That's an interesting one. And solvent preferences. Okay? So what we're trying to do is look at those main categories and say, what does it mean? If I'm in an SN1 reaction, what do I want the substrate to be? Well, according to this, I want the substrate to be tertiary. If I'm running an E2 reaction or an E2 mechanism, what's the characteristic of my base? It had better be strong. Okay? Not even just lowercase strong, like capital letters strong, because it's super, super important for the E2 elimination. So if you know what a base is, by looking at your structure, you can say, oh, that is a strong base. That suggests I'm following an E2 mechanism. So it's applying all of those definitions out to these larger systems. Okay? If that was it, that wouldn't be too bad, except we also get what I'm calling complications of each of those reactions. The SN1 reaction results in the loss of stereochemistry. So if you started with a stereocenter, when you run the SN1 reaction, it disappears. Okay? Which you could be, oh, that's nice, except the only way it disappears is that it produces two products. And those two products happen to be enantiomers of each other, typically. So when we talked about chirality, you have to be able to look for these things. Okay? The other big complication with the SN1, if you think you're doing an SN1 mechanism, you are also running an E1 mechanism. Well, that's not a big deal. It's not like they generate different products. An elimination resulted in pi bond. Does the substitution result in the formation of a pi bond? No. So if you're running an SN1 mechanism, very often you get an elimination product at the same time. What does that mean if we moved into the lab? I now design an experiment. In that experiment, do I want to use an SN1 mechanism? No, because it'll form the elimination product. So when I go through to do my experiment, not only do I get the substitution that I wanted, but I lose some of my reactants to this other junk that I didn't want. My yield necessarily goes down. So synthetically, the SN or the 1 type mechanisms are not helpful. Right? We get a reduced yield. So that means we would push into the 2 type mechanisms. But what happens within the 2 type mechanisms? SN2, if you started with an R stereocenter, it becomes S. It inverts. Right? So we'd have to design our experiments to watch out for that inversion if that's going to become a problem. Right? In the E2 mechanism, right, we have to have this thing known as anti-alignment. Oh, anti. What was anti in reference to? Oh, Newman projections. That's why we talked about Newman projections. To understand our product possibilities from the E2, I need to be able to evaluate Newman projections. Right? We end up with cis as possible products, and you end up with these 2 fun names that pop out of this, which I'm not a big fan of. So I can barely remember anybody's name in this classroom, right? Why would I remember a couple of dead guys? That's not true. I know everybody's name. Zaitsev and Hoffman, okay, they got to rubber stamp their name to individual reactions because the products produced were theoretically different from what was expected. Okay? That different thing is actually bad. Zaitsev literally just rubber stamped his name on an obvious reaction. Hoffman got to stamp his name on it because it was an unobvious reaction. Okay? Why did Zaitsev get to stamp his name if it was such an obvious reaction? He was first. Okay? And long before we even knew anything about electrons. So, I mean, fairly legitimate in a certain extent. You were able to do some pretty awesome predictions, and you didn't even know that we had electrons and protons. Okay. Still not worth memorizing. So, substitution. Let's go ahead and take a look at our substitution reaction. We've got an example here. Those people that were in lab on Monday, I would ask that you kind of hold your tongue on this because you've already seen this. Those of you that are taking lab on Wednesday or today or aren't in lab, think about these questions. We're looking at the reaction. We want to decide what bonds were broken or made. Or said more generically, what changes happened. Now you had a moment, Anthony, you want to jump in? We broke the C to the I bond. Somebody else want to jump in? What's that?
Did you move the electrons from Cl over to create a new bond with the C?
We made a new bond between the carbon and the chlorine. Okay. What way is the what? We're ignoring that for good reasons. Okay. What Bree added on top of what Anthony was adding was saying something about how the electrons moved, okay? Which actually gets us into the kind of the next stage. What are the possible ways that this can occur? Okay? We really just want to address first what things changed. Now that we know what things changed, how could those possible things happen? Well, we have two things that changed. What are the possible ways that those things could have occurred? So if I take a coin and I flip a coin, I got heads and tails. Okay, just a single coin. What are the possible outcomes that I could get? Just heads? Or just tails? Or, I said one coin. You flip the coin and it magically went poof, stood perfectly upright. That's fair. I can do that. So if we go through and take a look at our two options, we could have gone through and broken first, then we could have formed. Or we had the magical result. That's supposed to be black there. The magical result where they both happened at the same time. Or and you might be saying, well, that can't happen. I don't care if it can't happen yet. I want to address what are my possibles. Once I have the possibles, I can evaluate them. I could have formed and then broken. So there's only three possible ways this reaction could happen, okay, if we're looking at moving two electrons. Okay. Of those three possible ways, does any one of them just scream, nope, can't do that? Okay, 3 can't happen. I cannot form the bond between the chlorine and that carbon first. Why not? It would exceed the octet on the carbon. So I can ignore that last option. So really I only have two options. So what I would then go through and do is say, well, what happens? How would the electrons move? Which is what Bree was adding in when she talked about making the bond. Chlorine sharing electrons with that carbon. Okay? If we look at step 2, or version 2, we make the bond, our arrow is already shown, at the exact same instant that we break the bond, which means I need that other arrow shown. The result is I do it all in one step. If I break then form, I'm now doing it in 2 steps. Once I have the mechanistic results, I can now start to evaluate those pieces. Break that down into the subcategories and say, how does this all shake out? What does that logically mean my possible products are? What does that logically mean I need for this or for that? Okay? Before we move on to the elimination, let's clear, no, I don't want to clear all that away. Just break that away. Let's evaluate the pieces of the substitution reaction. Okay? Again, those of you on Monday have a little bit more of a hint here on this, and you can feel free to jump in with some answers. What pieces are involved in this reaction? We have a substrate. We have the leaving group, and this gets weird. The leaving group is iodide, but iodide hasn't left from the structure yet. So where can I label the leaving group? After it's already left. That is now my leaving group, which you'll always see me abbreviate as LG. What else do we have? We have a nucleophile. We have the species that shared electrons inwards. Right? And now the fourth one is the tricky one, because the fourth one rarely gets included. What is the fourth one?
Solvents.
The solvent. So every time we look at a substitution reaction, what we need to be thinking about are those four components. What do those four components mean about the mechanistic options? Break, then form, or do it all at the same time? So it's a question of finding that balance and evaluating each of those pieces and matching them up. Okay? What happens when we switch to the elimination? What things changed? Now everybody can answer this one. Nobody has an advantage here. We broke the carbon X bond. Okay, we could say we formed the pi bond. What's that? We also broke the carbon-hydrogen bond. Okay. For those of us keeping score, we might say, well, this now becomes a lot more complicated in the substitution because 3 different things have happened. Is that actually true? How many different things happened? Still only 2. Why is it only 2 things? I broke 2 bonds and I made 1 bond. That sounds like 3 to me. What happens if I break off atom X? Which is more electronegative, carbon or X? X, which means X is likely going to take the electrons, which means that carbon is what charge? Which is more electronegative, carbon or hydrogen? Carbon, which means when that hydrogen-carbon bond is broken, the electrons are left behind and we have that negative. What structure did I just draw? I just drew the product. Those are resonance contributors of each other. The formation of the pi bond is merely a resonance. Okay? It was already there to begin with. I only did 2 things. I broke hydrogen and I broke X. That's it. 2 things happen. I get the same now possible options that we had with the substitution. Do I break atom X first? Okay? Then H. Okay? Do I break H first? Then X. Okay? Do I do it all at the same time? Okay? So I get lots or 1 extra possible option. But that last one becomes a bit tricky. Why would the last one become tricky? Okay, let's look at the first one. We break atom X first. Right? We'd end up with that intermediate. In option 3, we're saying we break the hydrogen first. Is carbon-hydrogen an easy bond to break? No. Is carbon X an easy bond to break? Why is carbon X an easier bond to break? There's a difference in electronegativity. So to break that carbon-hydrogen bond, I am breaking the strongest bond I have accessible. And I'm breaking that bond first. That doesn't really resonate well. Okay? Why is it not a problem to do it second? Well, if I break that bond off, what can I do with the electrons? I can stabilize them through resonance by sharing them with that positive charge. Okay? So it's a question of how we generate stable intermediates. If we break the carbon-hydrogen bond, we're now going to a much, much, much higher energy state. If we go to a higher energy state, what does that mean about likelihood? Not likely. That last one is not a very good mechanistic step. We're again only looking at 2 options. Okay? If we slide backwards a whole bunch of slides here, which I'll probably regret. I won't regret. For substitution, we said how many possible mechanisms? 2. We call them SN1, SN2. We just addressed those. For elimination, we said how many possible mechanisms? 2, and we have E1, E2. Those mechanism names are ultimately coming from someone just saying, well, what things changed? How does this work? The elimination offered an option, but it was not a realistic third option. Turns out it's so not realistic that it doesn't exist. Okay? So, what we'd then be evaluating are the elementary mechanistic steps, labeling what happens in each of those. Okay? For the number 2 type substitution, it gets its own mechanistic name because it's a simultaneous reaction. Everything's happening at the same time. Super cool, super fancy, so we name it SN2. Because it was substitution and involved a nucleophile, and it was the number 2 mechanism. Oh, that's a little bit weird. That doesn't seem to make any sense. Okay? There's a reason behind that too. We'll get to it eventually. E2, elimination. Why does it not say EN? There's no nucleophile in the elimination reaction. It's just an elimination, and it was the type 2 mechanism, okay, where it all happened at once. Where's the SN1 and E1? They aren't up there. Why are they not up there? They required multiple mechanistic steps. The SN1, what was the first thing that happened? We broke a bond. Step 1, heterolysis. Then what did we do? We formed a new bond, coordination. What happened with the E1? As a hint. First step, heterolysis. We broke a bond. Then what did we do? We did some kind of elimination. What did we eliminate? That's a trickier question. No, the leaving group was our heterolysis. What did we break off? We broke off hydrogen. What charge was the hydrogen? Positive. Is hydrogen better labeled as an electrophile or a nucleophile? An electrophile. Does anybody have any problems with that? I do. Electrophile is by definition not hydrogen. I really don't like that definition. They're using it as a broader category. Maybe it's better to call it a Lewis acid elimination, okay, and then a Lewis base elimination, okay, but it kind of works. So our SN1 and our E1 are involved in those mechanisms, but we have to combine multiple mechanistic steps. Okay? What are you looking at?
Why is there a hat?
Come on. Why is there that hat? Sherlock. It's the Sherlock. You are uncultured. Thanks, Tristan. If we take a look at the simultaneous elementary steps, this is the SN2 and the E2. Bond, cleavage, and formation happen at the exact same time. So if I go through and had to add curved arrows to the top of these, I need to have the electrons from my iodide come in at the exact same time as my leaving group leaves. So there's my curved arrows. One mechanistic step. Beautiful. What happens in the E1? Or sorry, E2? I need to break the bond. Well, the leaving group can leave. But I also have to break what? A hydrogen. So that is kind of good enough. Okay? But remember, we're making a pi bond, which is higher in energy. How can I ensure that I get a large concentration of that pi bond? The leaving group is going to leave on its own. The hard part here is breaking the hydrogen off. Why? It's a non-polar covalent bond. So I need something to help break that bond. What's the hydrogen coming off as? As a positive, which means this species is acting as an acid. It's a horribly weak acid, but it's still acting as an acid. How could I speed that reaction along? I could bring in a base. So the base can attack the hydrogen, removing the hydrogen at the same time the electrons come in to form the pi bond and kick out the leaving group. So we end up with a few more curved arrows. Okay? So now that we have the mechanisms, we can evaluate that pesky 2. Okay? Which gets into everybody's favorite of all favorites, 152. And we add another level to it, everybody's favorite of favorites within 152, which nearly everybody seems to forget that they were actually taught as the first unit of 152, which was kinetics. So we're looking at the speed of a reaction. The speed of a reaction is dependent on the slowest step. What is the slowest step in the SN2? There's only one. So by definition, that step is the slowest step. That is the one that's going to determine the speed of the reaction. Speed is also known as rate. What is the rate expression for that slow step? Those of you in Monday are cheating. You've got the rate constant times the concentration. Products over reactants, there's a reason I'm not writing that. That, unfortunately, is the equilibrium. Wrong answer. You call me savage. Products over reactants is the equilibrium constant, which is derived from the rates, but it is not the rate expression. When we're looking at the rate for a reaction, it is almost always dependent solely on the reactants involved in that step. What are the reactants in that one and only step? Our nucleophile, which in this case was iodide, and the substrate, which was that big long thing. BR? What is the molecularity of this reaction? What the hell is molecularity? Yeah, that was 152 too. Okay. There are 2 species involved in this step, which makes it a bimolecular reaction. Bi is known as 2. Why is it called SN2? Because there's 2 reagents involved in the rate limiting step. It comes from the rate law. What happens when we move to the E2? What is our slow step in the E2? There's only one step. So it, by definition, is my slow step. My rate will be dependent on my rate constant, that's a lowercase k, times the concentration of the reagents involved. What are the reagents involved? Well, my substrate and the base. The E2 mechanism relies on the base. How many species are in my rate limiting step? 2. So it is known as a bimolecular reaction. It is now labeled E2. Okay? However you want to remember how 2s and 1s are associated is up to you, but that's where the 2s are coming from. Okay? I guess I should have asked for questions. Were there questions? What about the M and the N? Good question. That's actually M and H.
I was talking about in the rate equation. Because I have it written here.
The M and the N in the rate equation.
Powers.
Oh, your orders. Sorry. So let me get that rate equation again. Rate equals Ka. So what is being asked about is the M and the N, the orders, which we will kind of talk about a little bit later. Do you guys remember how you figured out the order in 152? From an experiment. You had to look at a bunch of experimental data, and it was this big, long, nasty equation with exponents and logs and natural logs and shuffling and dividing and multiplying, and it sucked. Okay. There was another way to determine the orders.
Look it up.
Nope. The coefficients from the equation, but not any equation, the coefficients from the The elementary mechanistic step. What are we looking at in this equation? The elementary mechanistic step, which means the orders are the coefficients from my balanced equation. In this case, those orders are 1. I add those orders up, I get 2, that's the bimolecular. So it has to come from an elementary mechanistic step. Conveniently, what are we looking at when we determine our rates? We're always looking at the elementary mechanistic step. We don't have to do that 152 calculation stuff again. Yay! Okay. What happens when we move into the 1 type? In our stepped SN1 and E1, both of them will start with heterolysis, followed by either coordination as our bond making or the electrophile elimination as our bond breaking. Okay? The heterolysis generates typically very high energy intermediates. Why are they high energy intermediates? They're charged. Take it a step further. Let's take a look at our first step here. We got a bunch of arrows shown. Where's the heterolysis? That's our first step. We're saying what happens? The electrons go up here. What's the result? The I is not connected anymore, and so I heard someone say charges are why this is a high energy intermediate. I would argue the iodide isn't all that bad. So I don't accept your high energy intermediates based off a charge. The other structure is a high energy intermediate because no octet. Okay? So the heterolysis in our SN1 and our E1 will always generate a very high energy intermediate in the carbocation, okay? Which means I need to stabilize that structure for this reaction to be successful. If that step doesn't happen, I cannot complete to do the coordination or the electrophile elimination. I have to finish that first step. Okay? The coordination will neutralize that reactivity by the chloride donating electrons. Okay? And that gets us our coordination. How does the electrophile elimination neutralize that high energy intermediate? That hydrogen is removed. We took the electrons that were in that bond and we turned them into the pi bond. And we have our electrophile elimination. These were both the SN1 and the E1 mechanisms, so the 1 type. Why are they referred to as the 1 type? Well, maybe for the E1 you've got a hint. Did I show anything about a base? No. The base isn't actually relevant for the E1. Okay? I'm still breaking a pretty strong bond, so there's got to be a reason for why that's allowed to happen, and we'll address that. I don't need a strong base, though. In the SN1, do I have a nucleophile? Yeah. Do I have a substrate? Well, by definition, I have to, otherwise I don't have a reaction. So I still have 2 species. Why are these 1s and not 2s? Remember, when we looked at the 2-stepped reactions, what were we talking about? We looked at the slow step. If we keep our focus on the substitution, where's our slow step? Is it the heterolysis or the coordination? Why would the heterolysis be our slow step? It's the formation of high energy intermediates that don't have their octet satisfied. So if we happen to, I don't know, look at an energy diagram where we started with our reactant, where's our intermediate? Significantly higher in energy. Where's our product? Lower than everything. If we go and add in our arrows, which of those steps is the slow step? Well, that will be dependent on what? The activation energy for each of those steps. How do I determine the activation energy? top minus bottom. What do I get? I get put 'em. Put 'em. I can't believe that actually worked. That was kind of amazing. What are you referencing when you're saying top minus bottom? It's the distance between our transition state and our reactant. You guys already packed up, so you can't even take notes on that. That is our activation barrier for the first step. What is our activation barrier for the second step? The reactant of the second step, which is the intermediate. Which of those activation barriers is larger? The first one, which means the first one is the slow step. So I now look at the first step and I want to define the rate law for that. Rate will equal my rate constant times concentration of the reactants involved in that step. What are the reactants involved in that step? Isn't the nucleophile there? The chloride's not doing anything in the heterolysis step, which means it is not officially a reagent in that step, which means my rate law is rate times the rate constant times concentration of my substrate. How many reagents are in that rate expression?
1.
1, hence SN1. It's a unimolecular reaction. That was kind of amazing. Come on. Top minus bottom to randomly. That was kind of cool.